So today we'll get closer to do an actual calculation. So as I was saying yesterday, the main ingredients that you have to feed into the quasi-particle picture to have an actual prediction for entanglement dynamics are two. So one is the velocity of the quasi-particles, okay, which this, I told you the results. So this is for free fermionic models. This is the group velocity. Sorry, this is B. This is the group velocity, okay, calculated in the usual way. And then the second ingredient is the steady state entropy. So the thermodynamic entropy that you get from the GG that describes the steady state. So this is S, which is also a function of K, okay? So you have to determine these two ingredients, and then you plug them into the quasi-particle picture, and you can get out numbers. So let me consider free fermion models. So free fermion models are models that, in a way or the other, you can write down into this form. So you have an Hamiltonian, you have sum over K. K is quasi-momentum. Then you have some single particle-like energy, and then you have some fermionic operators. Okay, so it's diagonal. So of course, the model with that you start with usually is not written in this form. You have to diagonalize it. If your model is quadratic, you can always do that. So you can bring it into this form, either via Fourier transform or by a combination of Fourier transform and Bogoliubov transformation for quadratic systems, of course. Okay. Now, so this K is the quasi-momentum. So it's 2 pi divided by L, where L is your size of the system, and then you have a times J, and this J is an integer. Okay. So it's J 1, 2, blah blah blah, 12. And these B are fermionic, okay? So fermionic operators. So you have some anti-commutation relations. B dagger K, B K prime. This is equal to delta K K prime, okay? Good. So now when you write a model like this, when you diagonalize it, you realize that, so a key thing is that the occupations, which are written as so B dagger K, BK, these are preserved, okay? Because the evolution of these operators B is trivial. So key thing, so if you want to determine the GG, key observation, so GG is completely determined by the expectation value of these occupations over the initial state. So you have your initial state like this, psi 0, and then you have to calculate this expectation value. And once you have that, you basically have the GG. Okay? So in practice, so you don't need to do this. So the way you would do it for a generic model would be to take the density matrix of the GG, and then you have lambda k and k, and you would have to determine the Lagrange multiplier. So you don't need to, because you have already the occupations. So these are enough. So the GG is fully characterized by this occupation. So now, what is the occupations define a GG? What is the thermodynamic entropy of this GG? So result. So you have S, which is a function of these occupations, and this is the entropy of the GG. And this you can write in this way. So it's extensive, so it's proportional to system size, and then you have an integral over the momenta, and then you have some density of entropy. And what is this function h? So this function h has a very simple form for free fermions. So h of nk is equal to minus nk logarithm of nk minus 1 minus nk logarithm of 1 minus nk. Okay. So this is the function. Okay. Yeah. That's a good point. Yeah, I wasn't sure about making this comment, but I think it's appropriate. So yes, the occupations are non-local, but for quenches in free fermionic models, you can show that you can map these occupations to local operators. So this is a result of Maurizio Fagotti and Fabian Hessler. So I think I even have the reference. So Fagotti and Hessler. This is a nice paper. So it's a peer B, 87, 24, 5107. It's rather old, so 2013. So the thing is that it's much more easy to work with occupations, and then you can satisfy your. It's an important requirement that you put your local observables, but you know that it's possible in principle. Okay, so you are happy. Now, what is the physical meaning of this function? So I think it's good to explain this because it will also become useful for Benjamin and for Giuseppe when they will discuss thermodynamic entropy. So let's take a generic, a single particle dispersion. So we have some epsilon k. So to consider a case which will be relevant later, let me choose this specific one. Is minus cos k. Okay, this is the dispersion relation of the XX chain. Then if you write this, so in the first, you restrict to the first Brillouin zone, and then you have this, something like this. Now the momenta are quantized, so here you have some single particle-like energies that you can fill. And by filling these single particle energies, you can generate any microscopic eigenstate of this model. Now you want to demand that the distribution in the thermodynamic limit is given by this n of k. Okay? So how do you do that? So basically it's a simple combinatorial problem. So what are the number of ways to choose to occupy the single particle levels in an interval between k and k plus dk? So how can I do this? So the total number of available spots is basically this. So is L n of k dk. So this is the total number of ways of occupied, the total number of occupied levels that give this density n of k. Then you have also the holes, so you can put the holes, but for free fermions, basically the holes and particles are related. So you have 1 minus n of k dk. So this is the total number of spots that you can occupy. Of course, this is a free fermionic model, so basically this cancels out with this, and we have something that goes with L. Okay, and then sorry, here there is a factorial now, and then I can distribute the way I put the particles. So here there is L n of k dk factorial. And then you can also, you have to count the way you distribute the holes. And then it's L 1 minus n of k decay factorial. Okay? So here you have everything. Now what you do, you use Stirling, right? It's a very simple thing. So Stirling, which tells you that if you have n factorial, it's roughly n to the n e to the minus n. And then it's a simple exercise that if you do it, you get basically this function. Okay, so you get that the entropy is the integral, I mean, what's written here, basically, okay? So this is for free fermions. You can redo the exercise changing one of the assumptions. So you can ask that, you can impose that this n of k is not the same as, that is not related to the distribution of the holes. So now you have rho particle and rho holes, okay, and they are independent. In the simple fermionic case, rho hole is just 1 minus rho particle. If you do that, I mean, you can do it as an exercise. So the key observation is that now the total number of single particle lie levels is not given by this expression, but you have to use rho plus rho holes. Okay, and this will give an extra term here in the entropy. So actually, so this is one of the key things in TBA, so in thermodynamic Bethe-Ansatz. So, and if you want to read it, yeah, I think you can read the classic paper, Yang. It's J. Math. Fees. Then 115, 1969. So old classic. Good. So okay. Now we have all the ingredients. So what I want to do now is to consider a specific case. So very simple one. So I will consider the XX chain. So this is a very, I would say, the minimal model of spin chains. Is really the simplest spin chain you can consider. So the Hamiltonian is the following. So minus, so 1/2 sum over I from 1 to L. And then you have sigma I plus 1 minus plus sigma I minus sigma I plus 1 plus. Good. And this sigma plus and minus are the spin raising and lowering operators. So basically S plus, let me write in the Pauli matrices. So sigma plus is sigma x plus y sigma y. I guess there is a factor 2, I'm never sure. Well, it's the operator that takes the spin down at brings you to spin up, okay? And sigma minus it does the other way around. So this model is super integrable because it's mappable to free fermions. And to do that, you have to do Jordan-Wigner transformation, which I guess you know, but let me just write down the basic transformation. So e to the minus I pi sum over k from 0 to j minus 1. Then you have sigma j z, and here you put c dagger j. Okay, so basically you map the sigma plus operator to the fermionic creation operator, but since the spins are bosons because they commute while the fermions are anti-commuting, you have to put the stored Wien string. Okay, very simple thing. So these are fermions, these C are fermions. So you have Cj anticommutator Ck is equal to delta Jk. Okay, very simple. To diagonalize this, so to bring this into the, well, let me first write down the, so if you do this transformation, then you end up with this Hamiltonian. Okay, it's a simple tight binding problem on a ring, so you have just free electrons hopping around, and this you can easily diagonalize by going to Fourier space. So you define momentum operators. So let me put a tilde actually here, because otherwise it's not clear what I mean. So you define this operator, sum over j e to the I k j cj. So these are the original fermions in real space. Here you are in momentum space. So if you substitute this into the tight binding, basically you get that your Hamiltonian now is diagonal. So it becomes sum over k, it is minus epsilon k, c dagger k, here is a tilde, c tilde k, and epsilon k is really what I wrote before, minus cos k. So the single particle dispersion that I wrote at the beginning. Okay, now we have this model. We want to do a quench. Actually, it's very hard to make a quench in this model because there is no free parameter to play with. But so I think that you can choose a particular initial state. So here in the following, I'll consider as initial state the null state. So the null state is this state here. Well, it's the same, but anyway. Down, down, up, down, blah, blah, blah. This is not an eigenstate of the model, so you have some non-trivial dynamics. Okay, so how do you solve this problem? So first of all, you write down the null state in terms of fermions. And this is easy, right? Because we know the mapping from before. So the null state is this state here, in which you occupy with the fermions one every two sides. So let's say, for instance, C dagger 2, C dagger 4, C dagger 6, blah, blah, blah. You apply this on the fermionic vacuum. Okay. So what did I tell you before? So in order to get the quasi-particle picture, you need to calculate the fermionic occupations, the density of occupations in the initial state. So now we're going to do it. So actually, you can calculate something slightly more complicated. So you can calculate this object. Okay. So you can calculate this correlator. And this is a very simple calculation, because now you use the definition of the fermionic operators in momentum space. You substitute here, and you get this thing, this object. So j prime e to the minus I j k plus I j prime k prime. Okay, and then due to this structure, you get a delta j prime, but only, I mean, this term is non-zero only if j is even, because here you decide to put the fermions on the even sides only. Okay, now you can massage this with the straightforward manipulations, and you end up with a very simple answer. So 1/2 delta k prime plus 1/2 delta k or k prime minus pi. Okay, very simple. So as I said at the beginning, we are interested in the case in the occupation, so C dagger k ck. So if you do this, if you put k equal to k prime here, you get something super simple. You get that the expectation value of the fermionic occupation in the initial state is very simple. It's basically 1/2. So it's a constant. So it's a constant. So this is non-generic. So in general, when you calculate these occupations, you have a non-trivial function of momentum. It's just the state is so simple and the model is so simple that in this case you get this simple answer. Okay. So, but what do we get for the entropy? So if we take the expression for the entropy, okay, and we replace n of k with 1/2, we get that the contribution of the quasi-particles to the entropy is very simple, and this basically log 2. Okay, so in this problem, you have these pairs of quasi-particles, and they carry, if you want, the largest amount of entanglement possible, which is log 2. Super simple. Then the second ingredient, as I said, for free fermions depends only on the dispersion of the model. So for the velocity of the quasi-particles, you get sin k. Okay. Now you have everything. So you can use these two results. You can use these two results into you can plug in them into the quasi-particle picture. So you get that the entropy of a block is 2t integral to absolute value of v, t less than L. So dk over 2 pi s of k v of k plus Now, S of k is log 2, and the V of k is sine k. So now you can even integrate analytically this expression. You can get a moderately complicated formula, but it's, I mean, what is important here is really this structure, okay? We don't care about the details of this S of k on V of k. Okay, now, I mean, so it's important that to appreciate how this thing works, that you calculate, you compare it yourself with some exact results, okay? So in fact, this formula is valid, as I was stressing also yesterday, only for T large, L large, with T by L fixed. Okay, this is the scaling limit in which holds, and this is also the scaling limit in which the hydro approach that Benjamin will discuss in the next lectures will hold. But the model is free fermions, so you can calculate the full dynamics of entanglement entropy at any time for any system, subsystem size. So, and now I want to mention how you can do it. So the key result is that, so for free fermions, also for bosons, but I'm gonna restrict to free fermions. SA is calculable from the two-point correlation function. So here you have your system, then you have your subsystem A. So if you can consider the correlation matrix. See the gray X, C, X prime, where now X and X prime are within A. So I'm going to show, it's actually very easy, rather easy, that if you have access to this matrix, you can compute the entanglement entropy. And this is a huge simplification because in principle, for a generic model, the reduced density matrix of subsystem A contains, it's a 2 to the L times 2 to the L matrix, where L is the sides of your subsystem A. So for free systems, you can actually reduce the computational complexity of the problem really a lot, because this matrix is L times L. So this is actually a very nice result that is due to so it's due to Ingo Peschel. And it's actually a very short paper, so I think it's worth writing down the reference. So it's a J. Fisey, 36, L205, 2003. So a very rather old paper, but it's really, if you count the number of papers that use this trick, I mean, it's enormous. Okay, so how do we show this? So the idea is that we have this correlation matrix, we want to write the reduced density matrix for your subsystem. So since the model is quadratic, you can guess that the density matrix is of this form. So is okay. So it's of this form where this matrix H here is to be determined. So we don't know it, we have to determine it. So you have a matrix here, H, so you have this quadratic form. The thing that you can do to simplify your life is to diagonalize this H. So you can diagonalize H. So you can define new fermionic operators, AN, in this way. So where you introduce these functions, and now your row becomes diagonal. So by a choice of these functions, you can diagonalize the matrix H such a way that it becomes diagonal, and this e to the minus sum over k. Now here I chose epsilon k. This is not good. So new k, a dagger k, ak. Okay, now this matrix row is diagonal. Okay. Okay, now you can use this Now you can use this to compute the expectation value. I mean, to compute the correlation function, right? So the correlation matrix has to be equal to this, right? C dagger and Cm rho. Okay. Now you use you expand this C in terms of these A's here. Okay. And if you do a little algebra, you get this expression. Phi star Kn phi K prime n, then you trace a dagger k, here I have what? A k prime, I have e to the minus sum over k, new k, e dagger dagger K, AK. Now this matrix is diagonal, so you can perform very easily this trace. And if you do it, this thing here gets replaced by this object. Okay? And you have a delta, of course, k, k prime. So eventually what you get is that this sum over k phi star kn phi k m 1. Okay, this is C, but on the other hand, the matrix H became diagonal by using this transformation with these phi's. So H and M is equal to sum over k phi k n phi k star m, and then you have this new k. Okay, and now you see that you have a simple relation between the eigenvalues of the correlation matrix and the eigenvalues of this matrix H. Okay, so you have that. So you have that the eigenvalues. The eigenvalues of the correlation matrix. I think I used the wrong thing. Okay. Yes. So the eigenvalues of the correlation matrix that I called Z of k, okay, are equal to nu k plus 1 to the minus 1. Okay. Now you know this. You know that the reduced density matrix now is diagonal. So is e to the sum over k, sum nu k, and then you have a dagger k, ak. From this simple form of the reduced density matrix, you can calculate the entropy, because you see all the different momenta factorize. So, and you get this. So you get the von Neumann entropy, for instance, is given by this simple form. Sum over k, logarithm 1 plus e to the minus nu k plus sum over k nu k e to the nu k. This is basically taking this matrix and doing trace of rho log rho, and you get this expression. Okay. So to summarize, how do you calculate the entropy for a free fermion model? You take your correlation matrix restricted to subsystem A, you diagonalize it, you get the eigenvalues, then you use this expression to get the nu, and then you substitute in this formula. So very simple. Okay, so what do we need in order to do this procedure for the quench from the null state? So as I said, now you need only the correlation matrix. So I mean, what I said, it works at any, for any time. So if you have the correlation as a function of time, you can calculate the dynamics of the entropy as a function of time. The only thing that you need is the correlation matrix. So you need G of t x prime. Okay, so this is C dagger x, C x prime. So, and both of these C's are function of time. Okay. Okay. So, but we calculated this object before in momentum space, right? So, if you look at your notes, so we calculated this. This was equal to 1/2 delta k prime plus 1/2 epsilon k. So we calculated, sorry, at t equals 0. Okay. So at t equals 0, basically you don't have this phase factor. Okay. So since these operators evolve trivially with the phase at generic time, so the delta k prime remains the delta, and here you get this extra phase. Okay, simple thing that you can check. Now it's trivial to go back to real space just by doing inverse Fourier transformation, and if you do this, you get this plus a simple exercise. So you go back to real space and you end up with this rather simple expression. So you see you have two contributions. So you have one which is delta x prime, and then you have this oscillating factor, so which oscillates with the parity of the sides, because it simply reflects that the null state has this alternating pattern at the beginning, right? So it's just that. Okay, now you have everything. So you have the correlation matrix. You can restrict it to your subsystem A. You can diagonalize it. You can calculate the eigenvalues. You can apply this formula. You get the entropy for any time and for any sides of your subsystem A. So you can plot it. And now you can compare it with the quasi-particle picture, which I gave you some time ago. And you check in which limit these two results match. So the best way to do this is to do a scaling plot of this form. So you plot the entropy divided by your subsystem size, because at infinite time you expect the entropy to scale as with the volume of your subsystem, and then you plot it as a function of t divided by L. So if you do this, you should see something like this. So you have SA divided by L, then here you have time divided by L. So you will have your quasi-particle prediction, and then if you use this strategy to compute the exact lattice result for the phenomenon entropy, you will have some curves that go like this, and then as you increase T and L, but keeping T by L fixed, you should see that this curve approach this quasi-particle picture. Exercise, check that. So you can also have fun checking how these different curves approach the scaling limit. You can also ask other questions and so on. Okay. Okay, good. So how much time? Yeah. That's a very good point, thanks. Yes, so for free fermions, I really should say that. So for free fermion models like XX, XY, or Ising chain, you can do the calculation analytically, deriving the quasi-particle picture ab initio. So basically what you do, you have you work with the correlation matrix. So it's really a very complicated calculation, but it can be done. And it has been done. So, and actually, so the main result is in this old paper. Is a 2008 paper, Maurizio Fagotti and Pasquale, and it's really the paper that opened the way to this type of results. We all owe something to Maurizio in a way or the other. Okay. Yes. So how much time do I have? Ah. Okay. Yeah. Okay. Yes, now, so the final thing that I have to do is to consider interactions. So an interaction is really what is not in Maurizio's paper. So now let's go to interacting case. So to deal with interactions, so I will focus mostly on the XXZ chain. So XXZ, which is, if you want, a generalization of the Heisenberg chain that Benjamin introduced this morning. 1 over L. So for delta equal 1, you recover Benjamin, the Heisenberg, the isotropic Heisenberg chain. So this delta is a real parameter that you can tune as you want. So the model is integrable for any delta. So, and it's solvable by beta ansatz. So, and here I really would like to have a minimal introduction about beta ansatz solvable models. So, and I'll try to be as basic as possible. So essentially, beta ansatz amounts to choose a good, indeed, ansatz for the wave function, for the eigenvectors of this chain. And since for any delta, So the model commutes with the total magnetization. You can decide to fix the total number of, let's say, downspins or upspins, depending on your taste. And let's consider the sector, I mean the eigenstates, with the fixed number of downspins, m. Okay, so m is an integer; it's the total number of downspins. So the beta ansatz for this, for the eigenstates of this model, is this. Okay, so this is pretty generic. So you have a sum over the positions. Xi are the positions of the downspins in the system. All the remaining sides are in the state up, okay, upspins. And then you have this amplitude, which depends on these coordinates, x1, x2, and xm. Okay, so the beta ansatz, in the beta ansatz, you write down this amplitude Okay, so here the sum is over the permutations of the labels I, okay, the m labels of the particles. And then you have this term here. So you see, if you forget about this is just like for free particles, right? But you have this term, which depends on the momenta, and it encodes information about the scattering between the different particles. Okay, so this is an ansatz. So you have to substitute this ansatz in the Schrödinger equation. And if you do that, you get some quantization conditions for this case. So in the free model, these k are just 2 pi by L, like J, like in the XX chain. Here the model is interacting, so these k's are non-trivial. And the equations that determine this case are the beta equations. Rafael. They are very simple to write, but they are very complicated to solve. So first of all, so you have a set of m equations, one for each k. So you have m equations, which are non-linear, because it's manifestly non-linear, right? Okay, so these equations were derived for the first time in 1931, I think. And they still have surprises. So I think we'll go on studying beta equations forever, fortunately. So another thing that I want to say is that, so these equations determine the momenta, well, quasi-momenta of the quasi-particles. So what is the energy? So if you have a set of momenta, okay, that you get from solving the beta equations, actually the energy, so each set of momenta characterizes an eigenstate of the XXZ chain. What is the energy of this eigenstate? Okay. So it's a very simple function because you sum over this momenta independently. And you see that the shape of the single particle dispersion is the same as for XX, it's just a cos k. Here, sorry, I'm forgetting some additional factors which depend on delta, but which do not depend on momenta, so they are not important for now. So you see, a thing that I really would like to stress is that the dispersion is the same as for free particles. However, where are interactions? Interactions are in the fact that the momenta are not equally spaced. So the particles fill each other. So these are not trivial. Okay? You have to go through the beta equations to get this single particle-like energies. Okay, so I think for now, I think it's a good point to stop. Yeah, in the afternoon, I will tell you how to generalize the quasi-particle picture for interacting integrable models, and then I will discuss some further applications of it. Okay, thanks.